Okay, this is my favorite topic. It is transmission line theory, which is part of electromagnetics. It was a fourth year course at my university, and I got above 80% on it. So it's going to be a little rusty because I have no idea what I'm doing, but let's see if we can figure something out. I got my little guide in front of me. So the first thing is what a transmission line is in order for a current I to travel, it's got to travel in a circle like that. And the circle usually has a load represented by a resistor or an impedance. And the impedance is Z equals R plus JL, where J equals square root of -1 always. So that is always true. Okay. So we have our I, and this usually comes from the generator, which is the source. So there's our source. And now we need a loop. So simply we can just go like this, and like this. And that's a closed circuit. We have a load. And we have a source, which means now electricity can flow in a circle. Now, what is transmission line electromagnetics? When this wave is so small that it changes with the length of this circuit, or when this circuit is so big that this wave still changes with the length of the circuit, then things don't behave linearly in steady state. Or we do have a steady state in the end, but it's always changing with time and distance. And then we have transmission line principles and effects. So an example is if this is 200-kilometer line and this source is 200 megawatts, WT equals so if the frequency, and you get frequency equals 1 over the period. So say it was like 60 degrees was the frequency. I don't know. 60 hertz. Hertz equals 1 over second. So 60 hertz, 200 megawatts, 200 kilometers. That means our AC source is not going to look like this or like this. -200 plus 200. Our AC source is going to look like this. Whee! Over here it's going to be plus 200. Over here it's going to be -200. Because it takes time to travel down the line. Because our source is in fact at a frequency and wavelength. So the wavelength of the source is varying by the time depending on the length of the line. This effect also applies in microelectronics, where the frequency is so high that the wavelength is so small. So even a 1 centimeter strip can have all these transmission line principles. And simply, we don't draw a circuit like that, we use guides. So in a microelectronic circuit, you have the bottom of the phone, which is the substrate, the plate. Then you have a dielectric, which is an insulator, a strong insulator. That's why it's called a dielectric. And then you have the top conducting plane. And what it does is it essentially goes like this, because this is ground. That's ground. And current travels along this path, and you essentially got two plates because now there's a separation. However, the separation has an effect of a inductor and a capacitor. It's got this at every distance Z. So every increment of Z, we got an induction and capacitive effect between the two dielectrics and our propagation of current. Now for a transmission line, what's the answer? For a transmission line, we have the telephone poles, not the telephone poles, the transmission lines where the transformers are. So where our transformers are, and there's our line. And the second half of the circuit is in fact the ground. So the ground. So we get this transmission and capacitive effect between the line and the ground over 200 kilometers. Over 200 kilometers. Now, how do we model this? So we model it like this. This is the model. So we have this, which is V equals VO E J W T, and then we have R with delta Z. We have an induction along the line. That's what my guide says that I'm looking at. We have our transductance, delta Z. And we have our capacitance, C delta Z. And we have our V Z plus delta Z T. So as we can see, this is our source. Our output is a function of Vz plus delta Z, and this is T. So function of time and distance. So the key is our voltages and our currents, and this is I. Once again, Z plus delta Z T. Our currents are a function of the total length of the line, or wherever we are, plus the increments and time. So it changes with location and time, because time means the wave is always changing, and location, where we are along the line. And to analyze this circuit, let me look at my guide here. I kind of remember it, but gonna skip a bunch of stuff. Let's see here. The derivative as the limit goes to 0. Yeah, so V voltage at a point Z equals a positive wave. This is very neat and interesting. A positive wave times e to the negative gamma Z plus a negative wave, e to the positive gamma z. So because a natural phenomenon is when this gets to our load, remember this is the ground and this is the top or dielectric, and that's the bottom plane and that's the conducting plane. When the source gets to the load, it actually bounces off of it because it never reaches it at the level it's supposed to stay at. It's a wave. So remember, when a wave hits a object, it bounces backwards. That's what happens to waves, because it's not a steady voltage anymore, it's a wave. So when a wave gets to the end, it bounces back. So the formula is the positive wave, VO the negative wave, and this is the shifter, E gamma Z and E positive gamma Z. That gamma is equals alpha plus j beta equals square root of r plus j ohm L times G plus j ohm C. So that's the gamma. So gamma is alpha, some alpha plus j beta, which is the square root of, now this is the natural impedances of the line, the natural fucking characteristics of the line. So the line has a natural inductance and capacitance and a transductance and a resistance. And when you group them into a binomial of R plus JL times G plus JC, take the square root of that, that's going to equal alpha plus J beta, which is our gamma. And then you have E gamma Z. So you always need a location. So at the location Z, we have a forward wave times our scaling factor with Z. And this kind of changes the phase. So this is the phase. This is the phase. And that's the amplitude. So we are scaled with the positive phase and the negative phase, with the location and a positive wave and a negative wave. So this is phase and this is amplitude. Amplitude and phase. And yeah, so anytime you want to find out where you are on the line, you go to this formula, plug in your Z, calculate the phase. Your amplitude comes from the amplitude of the source, and then you will get that. Now, not only is this the phase, but this is also scaling the amplitude, because the real component of this will affect the amplitude. So there is a real component. So the real component, now phase imaginary, I believe, I could be wrong, man, I forget. Phase imaginary, no, phase is, I don't know, but there's a real component and an imaginary component to this complex exponential, because there's a j here and a j here, and that's our gamma, which is in our complex exponential. And we have our amplitude, which will then be scaled, and our phase, which will then be scaled. And there's no phase, it's just a voltage. So the voltage of Z. So there is no phase. So it's just scaling real and imaginary voltage. So the imaginary part of our voltage and the real part of our voltage, and for the backward wave and the forward wave, is our voltage. Now, if we want V of Z and T, then I believe it would be a factor of VO e to the negative gamma Z T, or W T, which is our phase, or something like this. I don't know, something like that. We would have a component of time and Z in our forward wave and our backward wave. And that will tell us the voltage. So we have this, and it's based on this gamma, which is an alpha and a J beta of the natural characteristics of our line. And basically what we want to do is we want to like monitor how much reflections we're getting, because if we get too much reflections, it could explode, you know, or it could cause dangerous high spikes at certain loads. Wherever our loads are, depending on what the reflection is there, determines how big the wave is. So we want to design, and the only thing we can really do is change the length of the line. We can't change the material it's made out of. We're not going to be able to determine how big the wave is at all our loads based on just the materials and crap like that. So next to all our loads, we change the length of the line. We add a stub like this. And that just allows the wave to travel a little extra distance. And then when we get to our point, we are at our desired reflection. And the reflection is simply gamma equals negative VO over VO positive negative. Something like that. Something like that. Oh, this is gamma. Gamma. And that's the reflection coefficient equals V over V negative. Something like this. Let me check my guide once again. It didn't even cover. I covered a little bit extra than what the guide says. So I don't know. I'm just... In essence, that's what this is about, ladies and gentlemen. And I really like this course because when I had the tests and stuff, I got all this correct. I knew what I was doing. I had my reflections. I had my characteristic impedances of the line. I had my stub matching lengths. And I had my VZs and my VZTs, which also is I said T. Current, voltage. And two planes of conductance, the ground and the conducting plane. And we have these effects. We have our load. We have the frequency, and the wavelength is not matching the size of the circuit, which could be a generator on transmission line or a high frequency microelectronic circuit chip. So yeah, that is transmission line electromagnetics. Hope you feel inspired. That is my favorite thing to study. Because it's like a circuit, but you know, it's called electromagnetics because the waves actually are impacted by the wavelength, frequency, and size of the circuit, and they don't behave accordingly to a standard circuit, which is studied in electrical engineering. You need to take transmission line principles into effect when analyzing and determining and designing where the waves are going to be and how they're going to reach your load and whether your circuit's going to be stable or not and safe. So yeah. Peace.